Hello, everyone. In our previous session, we talked about a GPT-like large language model. Essentially, its fundamental task is next token prediction, and it's a transformer-based neural network trained on massive amount of data. And also, you can consider it's a pure stochastic model, right? Give the input, and then you get the output with a probability. Okay. Um, and we also mentioned that the input has to be converted into a number. Otherwise, your neural network cannot consume those input. Similarly, the output is also a number and then get decoded into a text, right? Don't mention about other type of input like audio, video, and image input. You also need to convert those pieces into a sequential of numbers and then generate the output. Okay, this process is called tokenization, and this will be the focus for our session. Um, let's look at this again. Last time we showed something called this tokenizer, like a playground. OpenAI published this one and briefly explained that like large language model just process using tokens. And then the model get to understand the statistical relationship between each tokens and then generate the next token in a sequence. And also you can see if you type something, it will give you like how many tokens does it have and what's the token IDs. Okay, it's split into a token and token IDs. Obviously, you will notice very interestingly for different model, the value will get changed, right? That means different model, they have a different kind of mapping. It's referred as like a vocabulary list. They have different kind of configurations. Okay, and another rule of thumb is like every 100 tokens is roughly 75 words. All right. Um, so we are going to look at this tokenization process. So these numbers are sent into the neural network and generate the output is also a number with the probability. And then you kind of decode back into a text. Okay, we will deep dive into the process and see how does this number being generated, because this is essentially kind of a static mapping based on a vocabulary list. So as a result, getting this vocabulary list is pretty much the prerequisite for the whole large language model inference process, right? So the big question is how do we get this mapping? All right. In the future, I'm going to use a different tokenizer because this one has the GPT-2 model. We will test on this one. Okay. Again, similar features based on the input sequence, it will give you the token or also the token IDs, right? You're gonna notice something very interesting is this. You have this space. This space normally comes as like a convention. It comes as the prefix, as a leading space, along with the next word. Okay, so with and without the space, you will get different output. For example, if we add a space before hello, um, this number will change. Okay, it changed to a different number. If we just type space, we will also a space itself will also have a number. Okay, this space will also convert it into a token. The value is 220. Okay, and we can look at this 220 and map this in the vocabulary list. Okay, another thing to mention is so the input sequence is not just English text, right? For example, I can put some Japanese language for happy birthday. It will still give us this individual token and then the digit and numbers. Okay, same thing for other type of things like emoji, right? This emoji is like 2 tokens to represent this emoji. Looks like this. All right. We are going to look at this vocabulary, and see how they are getting generated, right? Let's first look at their technical paper. Okay, in their technical paper, they explicitly mention about how they get this encoding process. The way they do is they use this something called byte pair encoding. Okay, at the byte level. So essentially, what they try to do is repetitively, they just merge some common and frequent pairs, which becomes a new token until they reach this vocabulary list. So the vocabulary list for GPT-2 is this number, so 50K. We've got 50K this static mapping. So the vocabulary size is this 50K. All right. Another interesting part is in this paper, we don't have to go very deep into the algorithm for the byte pair encoding, but something very interesting um, in the paper is it kind of mentioned about different choices, right? For example, you can do a word level encoding, or you can do a character level encoding. And then the problem for the word level is there are just so many words are not being used very often, right? So efficiency is a problem, and you are going to have many new words need to be represented in a special token, like called unknown token, right? And if you're gonna use this character level, that just means you need to cover this 130K Unicode characters, right? Which is not very efficient, and also it's very hard to find individual at the character level, find the statistical pattern between them. So in the end, OpenAI team they just do this subword level tokenization. So it just brilliantly cover most of the case, right? For example, say I have a new word called GPT E5, right? You can still tokenize in this way. I can keep changing E5 in this, right? I can still tokenize it, especially this IENS is a common suffix, and I can even do on GPT fineness, right? This on is also a common prefix. By doing this subword level tokenization, it make a very good balance between the word level versus character level. All right. Another thing in quick mentioned in the technical paper is they do this subword level tokenization. They kind of prevent the token to have multiple token for some common words, like you have a dog for your token, then you shouldn't have your dog with certain additional marks at the end, right? This byte pair encoding will prevent generating these redundant tokens, which is a good thing. You get to represent all your code very effectively. Let's quickly look at this one. Let's still look at this one, right? I mentioned before the prefix for the space, right? We also mentioned this when we tokenize a space, it gives us 200. We can right now open their vocabulary list and to understand what's in this 220. Like, what does this map to? Okay, so the way we can do it, there are two ways. First of all, is you can go to the repository in the GPT-2. This encoder is pretty much the tokenization process. What it does, it tries to load something called encoder.json. So this file is not in the repository because you need to explicitly download it using this script to download this encoder.json. I've already downloaded. I will quickly show you guys. In my code, it's this big mapping. You already see a big mapping from 0 all the way to this one, right? You already see that this one is a special token. End of text is kind of the end of sequence token. Once your GPT see this one, it will stop generating the next token. All right. This is one way to get this encoder.json. Another way is you open the Hugging Face, you open the file versions. You would be able to see something like tokenizer config, and vocabulary .json, right? So I already downloaded the raw file for the tokenizer, and also the vocab.json. I already downloaded in the VS Code. What's in this one? It simply give us an max length, like a limit for the sequence number. Okay, let's quickly look at this one. 220, right? Let's see if we can find it. Say for example, in this one, I already format this one. This one is pretty much identical to this encoder. If we find this one, we will find it's like this, right? This is pretty much the space. Okay, the space prefix. If we try to match this one, you see so many. There are so many kind of matching for this one. It's just a prefix. It's a space. But if you search for the for this one, it's actually not a Unicode for a space. Right? If you Google search, this just stands for this kind of like a G. It's not a space representation in the Unicode, which is very interesting to notice. Okay, let's come back to the tokenizer again. We already have this mapping. Let's look at this file. Okay, this tokenizer, you have a special token end of text with this ID, and then you have some other configurations, basically metadata, and then you have this vocabulary list in the end, which is exactly this one. Okay. On top of that, right, just quickly mention some other type of tokenizers. You can see different large language model, they use different type of tokenizer. For example, Google, they have this word piece tokenization system. This one is not open source. There's another called sentence piece tokenizer, is also developed by Google. This one is open source. Okay, and optionally, we can also train our own tokenizer from scratch, right? But before we do the training process, let's quickly look at the how does this tokenization work. Okay, so this is one of the notebook. So I can run it. I can load the GPT's tokenizer. You see, I have a space and space over here. When I print the tokens, it will give me the token result. At the same time, I can also convert these tokens into IDs. Right? And this is IDs. This is IDs. Right? Let's verify this. In this one, okay, not this one. These two should map to yes, these two. All right. You get the idea. But this is kind of like a two-step process. Normally, at the high level, you only need to do this once. Tokenizer.encode, and then you get the same result. Or you can also do a decode, right? Based on this ID, it will give you the original text. Both of them has a space. To train your own tokenizer, you can definitely refer to Hugging Face. There's a page to tell you how to train your own tokenizer. Specifically, it's like GPT-2's bipair encoding tokenizer. So it's a bunch of code, and then you do need to load your data set. And once you run this, it's gonna take a while. And then once you train your tokenizer, it will save it over here. You will get something called tokenizer, right? Looks very similar to this one we have for the original GPT-2 one. And then you can simply load it and then do exactly the same thing, right? Let me see if I can stop this one. It doesn't like it, but you get the idea. You can just load it and then run it again, generate your own tokens, okay? Yeah, this is pretty much the tokenization process, which is very important part, and it's like a prerequisite to run your large language model. Yeah, thanks for your watching.